Okay, so in the first part of dealing with this chapter, we introduced you guys to alcohols, and then we started talking about how we could form them. So specifically, we were dealing with reactions that we had already seen, how to make alcohols. And so this dealt with substitution reactions, which we had already seen. This also dealt with addition reactions with respect to alkenes, right? So this was hydration of an alkene. And so those were two different pathways whereby we could form an alcohol, depending on the reagents that we were given, right? So then we took this little segue into oxidation states, and the purpose of that was to introduce you guys to a new way or another way to produce an alcohol, and that is via the reduction of a carbonyl group, right? And so this can either be a ketone, right? So remember, as a ketone as a functional group is a carbon with a carbonyl with a double bond to an oxygen, surrounded by other alkyl groups, right? This can also come about via the reduction of an aldehyde as well, all right? So we're taking essentially this carbonyl group and we're reducing it overall to an alcohol, and that's the reaction that we're going to be dealing with now, right? So just to kind of get a hint as to oxidation states involved or how many electrons are going to be involved in this overall reaction, if we calculated the oxidation state of this ketone, right, using the method that we just used, we would find that the carbon here would get none of the electrons from this double bond to oxygen, because they would both go to the oxygen. It would get half of this bond to the alkyl group. It would get half of this bond to this alkyl group. So a ketone has a positive 2 oxidation state. When it goes overall to this alcohol, right, remember there is a hydrogen here, then the carbon's going to get both of those electrons from the hydrogen. It's going to get 1 electron from this carbon-carbon bond, 1 electron from this guy. So it moves overall to a 0 oxidation state, right? So what we're going to find is that a positive 2 to a 0, this is a reduction of 2 electrons. So we're dealing with essentially a 2 electron transfer process here, okay? We'll see the same thing for the aldehyde. So this is a ketone to an alcohol. We'll also see the same thing for aldehyde. Aldehydes don't have the same positive 2 oxidation state. Instead, this guy would have a positive 1, but when you reduce it to the alcohol over here, you're going to get a primary alcohol, which has a -1 oxidation state overall. So we're going to find the exact same 2 electron transfer process. Okay, so how do we do this then, right? So what are the various reagents we're going to need for this reduction reaction? So we have actually talked about one of the ways that we can do this already, and this came about when we were dealing with alkenes again, right? So if we had an alkene and we wanted to reduce it to an alkane, right? So we wanted to reduce it to an alkane. This was what we referred to as catalytic hydrogenation, right? We'd be adding hydrogens to carbons, two of the carbons on the double bond. So this guy and this guy to produce the alkane overall. So if you guys remember back to our addition reactions, the way that we could do that was via hydrogen. So this was hydrogen, and then it had to be in the presence of some sort of metal catalyst. So this could be platinum, this could be palladium, there was carbon. But with this reaction overall for ketones to alcohols, this can also be nickel. So again, we've seen this reaction before. We're aware of it. This is also a reduction reaction, taking an alkene and producing an alkane. And you guys can calculate the oxidation states to prove that. We're also going to find the exact same thing for our reduction of a ketone or an aldehyde to an alcohol, right? So this reaction also works with our ketone to our alcohol reaction, right? So the reagents here are going to be hydrogen. Again, it has to be in the presence of some sort of catalytic metal like platinum or palladium or nickel. Compared to our alkene reduction, this also has to have much higher temperatures and pressures, right, comparatively to this reaction. And so because of that, this is not used all that often. So not used often synthetically. And there's another reason why we will not utilize this reaction all that often, but it is potentially something that you could use for this overall reduction process. Okay, so then what are we going to use, right, if we don't use that very much? So I'm going to give you guys two different other potential reactions that are going to take your ketone or your aldehyde and reduce it to the alcohol. So the first one, again, is going to deal with a reagent that we have seen before. So again, going back to addition reactions, we have seen this sodium borohydride before. We didn't quite know what it did. We were just told during that oxymercuration, demercuration, it was a reducing agent. It is also going to be a reducing agent. The overall structure of this guy, or the main player in this overall compound, is the borohydride part, which is, as a structure, is this guy. This is boron. Due to the fact that it has 4 bonds, the hydrogen has a negative formal charge. And so then the sodium in this guy is just a counter ion to the borohydride. So this is actually the real player, borohydride, in this overall reaction. So this is going to be essentially what we would call our reducing agent here. Because again, if you need to reduce something to something else, then you need a reducing agent. And the real player, or the real reducing agent, ends up actually being the hydride that's present on the borohydride. Okay, so we're going to talk about the mechanism in a second. I'm going to kind of mention why, to get, or as a source of hydride, we have to use this guy as opposed to just hydride by itself. Okay, so this is essentially a 2-step reaction. It's the reduction via borohydride, but then there has to be a proton transfer step. So this is going to be our reagents here, our sodium borohydride, but this is in the presence of some sort of protic solvent. Again, a protic solvent is one that has hydrogen bonds, essentially. And the purpose of that protic solvent is to act as a proton transfer source, or as a proton source to protonate the negative charge oxide that we end up with at the end of this reaction. Okay, so this can be ethanol, it can be methanol, or it can be water, and they can all be mixed in with the sodium borohydride. Okay, so what is the overall mechanism for this guy? So again, if we go back to our 4 basic steps, what we're going to find in the first step is nucleophilic attack, right? And so notice we're dealing with the hydrogen. Normally when we see hydrogen, we think of proton transfer, right? Where a base goes out and gets the hydrogen, the electrons here are left behind. This is something entirely different, right? This is nucleophilic hydride. And so what's going to happen is the electrons that are in this bond are going to go with the hydrogen and attack the carbonyl carbon. That's going to form a bond between this carbon and this hydrogen, but because carbon can't have 5 bonds, it's going to essentially break these pi electrons. Are going to go up to the oxygen and form our first intermediate, which is this oxide ion, right? This negative charged alkyl type molecule, alkyl group. So again, this first step is nucleophilic attack from the hydride of the borohydride. Again, we can't end up with this as a negative charge overall. And so to get rid of that negative charge, to protonate it and form the alcohol, the second and final step of this reaction is a proton transfer from that protic solvent, right? So these guys are going to act as a base. They're going to go out. They're going to get the proton from whatever solvent we're dealing with, and the electrons are going to stay behind here. As a normal proton transfer step, we end up with our neutral alcohol as a product, okay? Okay, so one thing to mention here, again, we have the hydride of the borohydride acting as a nucleophile, and that is the first essential step of this overall reaction, this nucleophilic attack on the carbonyl carbon. This is one reason why we can't just use hydride as our nucleophile at this point in time. If you guys remember, hydride does exist, right? We can find it in the form of like sodium hydride or lithium hydride. But But when we talked about the difference between substitution versus elimination, hydride was not a nucleophile. It was only a very strong base. And the reason for that was the fact that hydride is not polarizable. And because it's not polarizable, it does not make it a very strong nucleophile. So this is why we have to use things like borohydride, because this is essentially our source of nucleophilic hydride. Okay, so one way to take, again, our ketone or our aldehyde and reduce it to an alcohol is via this sodium borohydride reduction. Again, this is going to be sodium borohydride in the presence of either ethanol or methanol or water, depending on whatever you want to use, right? So it's not all three of these, it's just one of them. And again, this is that source of proton in our second step in the overall mechanism. Okay, so we had catalytic hydrogenation as a possibility. We now have this reduction with sodium borohydride. There is a third reaction that we also have available to us, and it's very similar to the one that we just talked about. So in this third reaction, we use a different reagent that we haven't seen thus far, and this is something called lithium aluminum hydride. So if I write this out over here, the chemical formula for this is lithium aluminum and then hydride. The structure of this overall is very similar to the sodium borohydride. We have the aluminum hydride, which is similar to the borohydride. We have a negative charge on aluminum, and then we have lithium again as a counter ion. I would state that with kind of like a little caveat. The mechanism behind this reaction isn't super well understood, but they know that lithium does play a role somehow. So lithium's a counter ion. It does other things probably too, but we're not going to go into those other things at this point in time. Okay, so we can use lithium aluminum hydride. We also will abbreviate this as LAH. So you can either use this or you can use LAH. But this will also do this reaction just like the sodium borohydride. So we can take our aldehyde or our ketone and we can react it with the lithium aluminum hydride and get the alcohol as a product. One big difference is that this is comparatively, and why we would have two, is that this is much more reactive. And that's going to lead us to another reaction that we're going to talk about in a second. But because it's so much more reactive, it's super reactive with solvent as well with product solvents. So this will react violently. With any type of product solvent. So because of that, we can't put lithium aluminum hydride in our proton transfer solvent, right? Instead, we have to do it in two separate steps. So in the first step, we'll have, again, this reduction. We'll have to purify the product. And then in the second overall step, then we would add in our product solvent. This can be water. This, again, can be methanol, ethanol. And that's going to protonate and give us our overall alcohol at the end. After this reduction step, we would be left with that alk oxide. And so then in the final step, we have to add the water to get the alcohol as a result. So the mechanism here is the exact same as what we saw for the borohydride, except now the aluminum hydride is acting as that source of nucleophilic hydride. We're going to see that nucleophilic attack first, again forming our alk oxide ion. That alk oxide then has to be protonated via proton transfer step, where it acts as a base. It goes out to that product solvent, and we get our alcohol as a product. So again, two steps, exact same, nucleophilic attack followed by proton transfer. Overall for the reagents, so you do have to list for this reaction them in two separate steps. So one is the reduction followed by the workup, which is the protonation. Okay, so I had mentioned that this was a much more powerful reducing reagent. It's much more reactive. Because of that, we can actually utilize lithium aluminum hydride in a different reaction or a very similar reaction. So it's such a strong reducing agent. So again, as a reminder, we have this guy as our reducing agent, that it will reduce not only ketones and aldehydes to alcohols, but it will reduce also carboxylic acids as well as esters to alcohols as well. So we think about that, and we think about oxidation states. In a carboxylic acid, the oxidation state is a positive 3 because it only gets 1 electron from this carbon-carbon bond. When again we reduce it to the alcohol, we've got a hydrogen, it gets both of those, it gets both of those, it gets 1 from here. We're again reducing it to a -1 overall. So now in this reduction, we're taking a carboxylic acid to an alcohol. This is a 4 electron reduction, because in going from a +3 oxidation state to a -1, that requires 4 electrons. In our ketone or aldehyde to an alcohol, it was only a 2 electron reduction, right? So this is going to be essentially capable of a 4 electron reduction overall. It's the exact same thing with the ester. So this is again going to be a +3 oxidation state. This is a 4 electron reduction to a -1. So we're going to see the exact same thing. So this is 4 electron reduction. This is a 4 electron reduction. Okay, so we can do that, right? Lithium aluminum hydride, as long as there is an excess of it, can do this, because again, with respect to an excess, we need more than just 1 reducing agent. For every molecule, we'll need 2 reducing agents, because we need 4 electrons overall. All right, so then what is the overall mechanism? So we're going to do this for the ester. So I'm just going to take this guy, redraw it. So the first step is going to be very similar to what we saw before. We're going to find that we have a nucleophilic attack. And again, the nucleophile is the hydride on the aluminum hydride, so we can go ahead and draw that guy out. We're going to find that the electrons in this hydride are going to go ahead and attack the carbonyl carbon, which is going to push up the pi electrons here. And we're going to be left with our first intermediate, which is this alkoxide, where we have a single bond here, lone pair, lone pair, lone pair, negative charge. And we do have at this point in time this new hydrogen that we have added from that hydride attack. Now, normally we'd be like, oh, then we're going to follow this with a proton transfer step, but that's actually not what happens in this overall reaction, right? So now, instead, our second step in this overall mechanism is actually loss of leaving group. And the leaving group here is actually this methoxide, or this ether linkage, right? So what's going to happen is the electrons that are on our oxygen are going to come down, reform this double bond. What that's going to do is then kick out this methoxide as a leaving group. And so we had nucleophilic attack. This is going to be followed by loss of leaving group. And so our product at this point in time looks like this. This, again, is an aldehyde. And we've talked about, well, aldehydes are, of course, very susceptible to reduction via lithium aluminum hydride, right? So now we had a first round of reactions where we had 2 electrons being transferred. We're now going to have that exact same thing repeat, right? So the next step overall is nucleophilic attack from another lithium aluminum hydride. So nucleophilic attack, we've got our hydride. Again, that's not very clear. We're going to attack our carbonyl carbon. We're going to form the alkoxide group as an intermediate, right? And again, that hydrogen we've just attached is here. Now, this isn't going to kick out anyone. Instead, we're actually going to follow with that final step in the overall mechanism. This is when the water comes in, or the protic solvent, and protonates our product. So this guy is going to just be ended with proton transfer, right? And so at the end of the day, we end up with our alcohol. Again, these are the two hydrogens. We've got our lone pair. And again, this guy, fourth step overall, is proton transfer. Okay, and so that is the overall mechanism for reduction of either an ester or a carboxylic acid to an alcohol using lithium aluminum hydride. Okay. This is the only one, lithium aluminum hydride is the only reducing agent that's capable of doing this reaction. So if you need to reduce an ester or carboxylic acid to an alcohol, you need to do it with this reaction and not with the borohydride. Okay, so that is kind of like a little summary here of the three different reactions, that we just learned to take a ketone or an aldehyde and reduce it to an alcohol, okay? So again, why would you want to use one over the other? We already talked about how this isn't, the catalytic hydrogenation isn't super synthetically useful due to the fact that it requires high temps and pressures. No, we're going to write correctly, or we're not going to write at all. So this is, again, not super useful because it has high temps and pressures. Another reason why you would maybe choose not to do that is because it can also undergo that reduction of an alkene to an alkane. So let's say that you had a ketone, right, that also had an alkene in it. If you tried to reduce this guy to the alcohol, it would also reduce, if you use this catalytic hydrogenation, it would also reduce that alkene to an alkane, right? So if you actually wanted to keep the alkene, you couldn't use that reaction, but instead, sodium borohydride as well as lithium aluminum hydride are specific for reduction only of the ketone to the alcohol, right? So the alkene is not reduced in the presence of these guys. In presence, I just say it's not reduced. I think that's good. Totes. Okay, so that's 3 reactions. We're going to actually learn another one in a second. Before we can do that, though, we take a little segue into a thing called diols, right? So if you have a compound that has 2 alcohol groups in it, it is a special type of alcohol that is specifically referred to as a diol. So again, di stands for 2. A diol is essentially just 2 alcohols, okay? So again, this is a special type of alcohol. So if you do have a diol, it actually has different rules with respect to nomenclature, right? So for example, if I had a molecule or just a normal alcohol that looked like this and I wanted to name it, right, the first thing I would do is count the carbons. I would say my parent chain has 1, 2, 3 carbons. So 3 is propane, right? But because it has an alcohol, we will have the propane all. Remember, the E gets dropped here. E is dropped. And we end up with the OL to show that's an alcohol. To specify where this guy is, we would assign our locants. So here, this would be 1 propanol. Okay, so now, instead of 1 propanol or normal alcohols, let's say this instead was, again, a diol, right, where we had 2 alcohol groups attached to it, okay? So how does that change the way we name it? So we recognize the fact that we have 2 alcohols, so it's going to be a diol. Again, the parent chain is going to be the same exact thing with respect to just the alcohol. So it's going to be the carbon chain that contains both of the OH groups. For this guy, we would name it 1, 2, 3. And we would, again, have to specify where both of the alcohols are via the locant beforehand. So this would be a 1, 3. Now, the big difference here, again, is a propane as the parent, but we're actually going to keep the entire propane part, right? The ending is going to be diol to specify that it's a diol, but instead of dropping the E here, we're going to keep it and end it with DIOL to represent the fact that it's a diol. So if it has one alcohol group, we're dropping the E. If it has two alcohol groups and it's a diol, we're keeping the E and we're ending in DIOL. Okay, so again, diols, two alcohol groups to the molecule. They're their own special functional group. And so they get that, or we signify that using the diol as an ending. Okay, so then how do we prepare diols, right? So very similar to how we would prepare alcohols. If we had a diketone, right? So say we had a molecule that was a diketone or a ketone in an aldehyde, and we used any of the reducing reactions that we just learned, we would get as a product our diol. Wherever those ketones, wherever those carbonyls were, would turn into alcohols via these reducing reactions. Another specific reaction that produces a diol is, again, something that we've already seen. So one of the addition reactions that we talked about dealt with taking an alkene and making a diol, right, with two alcohols. This specifically was that dihydroxylation reaction. And again, depending on what type of diol we wanted, whether we wanted syn addition or we wanted anti-addition, depended on the reagents that we were going to use, right? So if we wanted those alcohols to be added on opposite sides of the double bond, then we went through that anti-dihydroxylation, where we took one of those peroxy acids, right? So we had a peroxy acid. We were given a couple of different options for that, right? So we just abbreviated that peroxy acid as RCO3H. Another one that we frequently would use was what was called MCPBA. Again, what that formed was an epoxide, which is that 3-member oxygen, like cyclic ether group. And then to open that epoxide and give us our final diol product, we used an acid, right? So this was our peroxy acid. It made that epoxide, and then to open the epoxide, we used an acid, and that gave us our anti-diol product. If instead we wanted the syn diol product, then we used that osmium tetroxide. It was catalytic in the presence of this NMO. Okay, so again, how do we prepare a diol? Well, we can either reduce a diketone, a dialdehyde, or we can take an alkene, and we can either undergo anti or syn dihydroxylation to get the diol product that we desire. Okay, so finally, there's going to be one last reaction that we're going to learn from how to produce alcohols, okay? Now, this is going to be very similar to what we learned with respect to the reduction reactions with the sodium borohydride or the lithium aluminum hydride, but it's going to be slightly different in the product overall that we get, okay? But again, this is going to be one more form of a reduction reaction where we could take something like a ketone and we could reduce it to an alcohol overall. Okay, now what is this going to involve? Okay, so the first thing we have to talk about is something called a Grignard reagent. Right, so we haven't talked about Grignard reagents thus far, and I know that I'm not pronouncing this correctly because it's French, and I'm sure it's like Grignard, something like that, but it seems to me like it says Grignard, so I've always just said Grignard reagents. So what is a Grignard reagent? Okay, so a Grignard reagent is formed when you take an alkyl halide and you react it with magnesium metal. Okay, that is going to form, again, your Grignard reagent. Now, what does that mean, right? What are we actually forming when we form this Grignard reagent? So notice that we take just our alkyl halide, which had a carbon halogen, a carbon bromine bond, and we turn that in to a carbon magnesium bond, okay? We're not going to be concerned with how this reaction goes, but just the overall product that we get, Okay, now if we think about in terms of this bond that is formed and we think about electronegativity differences here, normally we'd say, oh, carbon's not electronegative, but compared to magnesium, carbon's extremely electronegative, right? So there is a large difference in electronegativity here, where carbon is essentially going to be withdrawing the majority of the electrons that are in this bond towards it. We can characterize that as a polar bond, right, with these partial negatives on the carbon and this partial positive on the magnesium. But this difference here in electronegativity is so large that we can essentially treat this bond as being ionic, right? So that carbon has all of the electrons in that bond and magnesium has none, okay? Now, because of that, this carbon is fairly reactive, right? So this is essentially going to be a carbide or a carbanion, and carbide or carb and ion. And again, anytime you have a negative charge, especially on something like carbon, it's extremely reactive. This is going to be a very strong nucleophile. It's also a very strong reducing agent. And very similar to the hydride, it's also a very strong base, right? So each of those things, nucleophile versus base or reducing agent versus base, is going to do different things and it's going to have different consequences overall. And we're going to talk about that means in terms of these Grignard reagents. Okay, so because it is a strong nucleophile, because it is a strong reducing agent, Grignard reagents are capable of reducing our ketones or our aldehydes to alcohols, right? Just like we saw for the hydride reagents, right? Now, the difference here is that instead of forming a carbon-hydrogen bond via that hydride reduction, what we're going to be forming is a carbon-carbon bond between the carbon of our ketone and the carbon or the carbanion or the whatever we're looking at of our Grignard reagent, right? So again, one of these magical, mystical things that we talk about in organic chemistry is anytime we get to form a carbon-carbon bond, this is going to be one of those reactions that forms a carbon-carbon bond, okay? All right, so now, how does this work, or what is the overall mechanism? It's going to follow very similarly to what we saw for the hydrides, right? The reducing agents of the hydrides, which was the, again, sodium borohydride, lithium aluminum hydride. The first step overall is going to be nucleophilic attack, where our Grignard reagent, or our carbide or our carbanion, is going to attack the carbonyl carbon of our ketone or our aldehyde. Again, that's going to form our carbon-carbon bond here. It's going to push up the electrons in the pi bond so that carbon doesn't have more than 5 bonds. And we're going to be left as an intermediate with our alk oxide. Again, we can't end there because we have a negative alk oxide ion. So to produce our alcohol at the end of the day, we need to protonate that. We're going to do that via a second proton transfer step, just like we saw for sodium borohydride, lithium aluminum hydride. That proton transfer is going to come from some sort of protic solvent. So again, this can be water, this can be ethanol, this can be methanol. Again, our alk oxide is going to act as a base. It's going to go take a proton from that protic solvent, and we're going to end up with our alcohol. I can't spell alcohol very well. Alcohol at the end of the day. Okay, so exact same type of mechanism here. The big difference being that instead of this carbon-hydrogen bond, we're going to get our carbon-carbon bond. Right, so instead of adding a hydrogen there, we're adding an alkyl group, whatever the Grignard reagent is. Okay, so a couple things to note here. Very similar to what we saw with lithium aluminum hydride, our Grignard reagent, as mentioned, is a very strong nucleophile, so it's very good at this reaction, but it's also a very strong base, right? So this kind of has some consequences that we're going to need to discuss. So if we had taken our Grignard reagent, let's imagine it's some alkyl group, right? and we had reacted it with our ketone, and then we had put our water in, our protic solvent in at the same time, the preferential reaction would be for this guy to act as a base and to go and take a proton from water, leaving behind just the normal alkane at the end of the day, right? So this would be bad, right? Every time this reaction occurred, we would ruin our Grignard reagent because we'd just be turning it into this unreactive alkane, and this reaction would happen preferentially over this reaction attacking the ketone, okay? So because of that, we have to do this reaction in two separate steps, where again we have our nucleophilic attack, our reduction reaction occurring first, right? We have our alkoxide product that we have to work up, and then in the second step, that's when we're going to add in our protic solvent to protonate that alkoxide and end up with the alcohol at the end of the day, okay? Now, I know it's like, well, big deal, or yeah, sure, I'll remember that this has to happen in two steps, but it's also important if you actually ever have to utilize a Grignard reagent, and the fact that they are so susceptible to reaction with water that if you ever were to utilize one, you would have to also ensure that all water has been removed from the atmosphere around the reaction, because if it's not, they will react with the water and it will ruin your overall reaction. It will essentially just take away all of your Grignard reagents. Okay, so for example, like how would you utilize this? So I tried to mention earlier that the great utility of Grignard reagents isn't necessarily the reduction of a ketone to an alcohol, but instead is the formation of that carbon-carbon bond, right? So for example, let's say that you had a molecule like this, and they asked you, okay, how would you use a Grignard reagent to make the following compound, okay? So notice a couple of things. Number one, our following compound is an alcohol, so there's already been a reduction happening, and that reduction is going to come from that Grignard reagent, okay? So remember that a Grignard reagent is a compound that contains a carbon-magnesium bond, and that carbon-magnesium bond is going to attack the carbon that would have been present or would have contained our ketone or our carbonyl group, right? At the time, whenever that reaction occurs, we're going to be forming a carbon-carbon bond. So if we look at this compound and we look at what's attached to this carbon, we've got our alcohol, which we're going to ignore for right now, but we have three other carbon-carbon bonds, right? So we have our carbon attached to this carbon, we have our carbon attached to this carbon, we have our carbon attached to this carbon, okay? So we have a couple of different options for this overall reaction. There are essentially three different ways where we can take a ketone and we can introduce one of these carbon-carbon bonds, right? So for example, let's say that in my starting ketone, I wanted to start with this guy and this guy present, right? So let's say that we had initially a compound that looked like this, right? That already had this bond and this bond there. Right? And again, this is going to have to start with a ketone, right? Because we're going to be reducing that ketone to an alcohol, okay? All right, so if that's what I started with, right, then what I would be producing, or what I would be introducing in my Grignard reagent would be this bond, right? So this would be essentially formed from a methyl carbide ion or methyl Grignard reagent, right? That methyl Grignard reagent would be essentially in the form of, again, this methyl magnesium with the alkyl halide or the halogen at the end. Okay, this would be the Grignard reagent that would produce this carbide ion that would attack our ketone that would produce the alcohol, as well as this carbon-carbon bond. Okay, so again, with Grignard reagents, we would have our starting ketone. The first step would be reduction with the Grignard reagent, CH3MgBr. We would end up with our alkoxide that would have our new carbon-carbon bond, right? But to get rid of that alkoxide, to protonate it, we would have to follow in a second step with water, right? So one way that we could accomplish this is taking this guy, using the methyl Grignard reagent And following that in a second step with water, we would get overall as a product methyl OH, something that looked like this, which is again what we started with, okay? Now, that was not the only way that we could have produced that compound using a Grignard reagent, right? That's kind of up to us on how we want to go about this. We could have also said, well, what if instead I wanted to start with this compound, or this carbon-carbon bond, and this carbon-carbon bond, and I wanted to introduce this carbon-carbon bond, right? So then, instead, our initial starting material would have been this guy and this guy already there, which would have looked like this, right? And now we'd be introducing this guy, which would be a CH2, CH3, right? So an ethyl Grignard reagent. To represent that, we would just write that carbon ion, or that carbide, CH2, CH3, CH2 magnesium bromide. You could also just say ethyl magnesium bromide, just like you would have said methyl MgBr up here. That again is going to give us our exact same product overall with our OH, with our methyl group out here. But again, we would have to follow that with water as a workup. And then again, we're not limited here. We could have also just stated, okay, well, I actually wanted to start with this guy, and this guy, and this guy, and this guy, and I wanted to introduce this thing, right? So if I'd done that, then instead, my starting ketone would have looked like this. Now, the phenyl group would have been the Grignard reagent, right? And so again, we can represent this guy as just pH with pH with our lone pair of electrons, our negative charge. So here, our Grignard reagent would have been pH, MgBr. And then again, a second step would have been H2O. And we would have ended up with the exact same product. So there is no one way to go about answering this question. But you do need to recognize that if you're producing an alcohol using a Grignard reagent, the starting material is going to have that ketone wherever the alcohol is located. And it's also going to have present already 2 of the carbon-carbon bonds that are present in your overall desired product, right? You're going to be introducing one of those carbon-carbon bonds via your Grignard reagent. Okay, yeah, so hopefully that made a little sense. On this PowerPoint, I think I tried to speed things up a little bit, so I don't have I don't think I have a lot of questions for you guys to do. So if you see me come up to another example and you don't want me to just explain it, you may want to stop, try to answer it yourself, and then push play when you're ready to explain it. Okay, so there are a couple other little bits with respect to Grignard reagents that we have to go over. So number one, like I mentioned, Grignard reagents are very strong nucleophiles. They're very strong reducing agents, just like our lithium aluminum hydride was. All right, so remember that with lithium aluminum hydride, we could take a ketone or an aldehyde and reduce it to an alcohol. These guys were also able to take things like carboxylic acids, right, as well as esters. And also in a 4-electron process, so this required excess lithium aluminum hydride, they were also able to reduce those into alcohols as well, right? And in the process, what they were creating were 2 carbon-hydrogen bonds. So same thing over here for the esters, right? So again, lithium aluminum hydride was a strong reducing agent. If we had excess of it, we could take a carboxylic acid, reduce it to an alcohol. We could also take an ester and reduce it to an alcohol as well. And in that process, we were forming 2 new carbon-hydrogen bonds, okay? All right, so Grignard reagents can also do a similar reaction, right? So we can take an ester right, we can have an excess of whatever Grignard reagent we have, right? Again, we have our carbide, our negative charge carbon here. Or actually, let me put that over the carbon. So this, guys, where our negative charge is. This can undergo a very similar reaction, a very similar mechanism to what we saw for the lithium aluminum hydride. So again, we first saw nucleophilic attack, followed by loss of leaving group, right? So if this isn't ringing a bell, please reference the mechanism for the reduction of the ester to the alcohol for lithium aluminum hydride. This was then followed with nucleophilic attack. And then at the very, very, very end, we'd have that proton transfer step. And again, the only difference here with this mechanism is that nucleophile, instead of it being a hydride, is instead our carbide, our negative charged carbon, okay? All right, so we can take an ester, have excess Grignard reagent, and at the end of the day, end up with our alcohol. Again, this is a 2 reduction step, so we have 4 electrons being transferred. Instead of forming 2 new carbon-hydrogen bonds, though, in this overall reaction, we're forming 2 new carbon-carbon bonds, which again can be helpful sometimes if we want to make a new carbon-carbon bond. Now, note that I have talked about this with respect to the ester, but I have not talked about this with respect to the carboxylic acid, right? So for carboxylic acids, we actually cannot take a Grignard reagent and reduce a carboxylic acid to the alcohol like we can an ester. And there's a reason for that. That hinges on the fact that this Grignard reagent is a very strong base, right, as well as a nucleophile. And so because of that, this proton is fairly acidic comparatively. And if we put our carboxylic acid in the presence of our Grignard reagent, instead of there being nucleophilic attack and reduction of that carbonyl to the alcohol, we would instead just get proton transfer, right? And we would end up with our deprotonated carboxylic acid, which is boring and not useful synthetically, right? So because of that, we cannot use Grignard reagents to reduce carboxylic acids to alcohol. It is not a reaction that is possible. But we can do that with esters. Okay, so there's another kind of consequence to this basicity of the Grignard reagent, and that's the fact that we cannot have a Grignard reagent that has even a mildly acidic proton on it, right? So for example, let's say that I had this guy, so we have our, let's say, propanol. And again, with Grignard reagents, they have to have a halide on them to make them a Grignard reagent. Let's say I wanted to utilize this guy to make a Grignard reagent, right? So again, notice the magnesium isn't there. We first have to react these guys with magnesium, right? When we do react these alkyl halides with magnesium, they will then form the Grignard reagent. So we have bromine, magnesium. There is, I don't know why this is not zooming correctly. So we had 1, 2, 3 carbons here. We have 1, 2, 3 carbons here. And again, we're wanting to take this alcohol and turn it into a Grignard reagent by, again, just reacting with magnesium, okay? Now, there's an issue with this guy. So as a reminder, this is the bond that is polarized, right? And so this is the carbon that has that negative charge and that pair of electrons. This is the basic or the carbide or the nucleophilic carbon, okay? If this is in the presence of even a mildly acidic proton, all this is going to do is just act as a base and deprotonate this guy. And so at the end of the day, that's just going to ruin our Grignard reagent, and all we're going to end up with is a deprotonated alkoxide that isn't going to be able to do any of the reactions we want to do in terms of reducing carbonyls to alcohols or forming carbon-carbon bonds, okay? So unfortunately, that's an issue that we have to consider, but we do have a way around this, right? Where if we do have a compound that does contain an alcohol or a mildly acidic proton, there are ways that we can take that and still utilize this reaction in producing a Grignard reagent and reacting with a ketonelaldehyde and producing our new carbon-carbon bond. We just have to take a few extra steps to account for the fact and to prevent this overall deprotonation reaction. All right, so then how do we do that, essentially, right? So what's going to happen is we're going to take our starting material, our alkyl halide with the alcohol before we ever react with magnesium, and then we're going to essentially put it through what is called a protecting step. And in that protecting step, we're going to use something called trimethyl silyl chloride. So we abbreviate this guy TMSCl. This is going to be using triethylamine as a solvent, so ET3N. And what that's going to form is essentially going to react with the hydroxyl of the alcohol. It's going to deprotonate and it's going to form what is called trimethyl silyl ether. Okay, and so we abbreviate this guy in the green box as OTMS, which is shown here. Okay, so again, before any of the Grignard reaction starts, before anything happens, we take our alkyl halide that has this alkyl group or this alcohol group on it that's super acidic. We're going to protect it using TMSCl in the presence of trimethylamine. It's going to form an ether linkage between the oxygen of the alcohol and the silicon of the trimethyl silyl chloride. This is not going to be susceptible to any type of reaction from the carbide of the Grignard reagent, right? And so then we're going to take this guy, we'll then react it with magnesium, and we'll move forward in an overall reaction. Okay, so first step is going to be to protect that hydroxyl group on the compound that we want to make a Grignard reagent into. After we protect it, by again reacting it with this TMSCl in the presence of triethylamine, we are then going to take it and react it with magnesium and perform our Grignard reaction, right? So we're first going to take this guy, react it with magnesium in a first step. That's going to form our Grignard reagent, OTMS, right? Then we're going to take our Grignard reagent, we're going to react it with our aldehyde or our ketone, right? So for example, let's say this is our aldehyde and our ketone that we're going to reduce. We're then going to form our alcohol as a product. Well, first will be ethoxide or the alkoxide, right, with our new carbon-carbon bond. So we have 1, 2, 3 carbons. We've got 1, 2, 3 carbons, so OTMS. And then again, so this is one reaction, this is two reaction, we have the reduction, and then as we mentioned before, we can't add water immediately because it would just react with our Grignard reagent. So then in a third separate step, we'll add our protic solvent to protonate our alkoxide, and we will end up overall with our protonated alcohol. But now the only problem is we still have this protecting group on here. Okay, so first step is taking our alkyl halide that has our alcohol, protecting it with this TMSCl and triethylamine. Once we're there, we'll then react with magnesium to form the Grignard reagent. We'll react it with our aldehyde or ketone to undergo that reduction. And then again, we'll react it with water in a third step to protonate that alkoxide product. Again, at the end of the day, we still have that protecting group on. And so then what we utilized is either acid or fluoride to deprotect, right? So we're not going to go through the mechanism of this, but just note that you can deprotect with either acid or source of fluoride ions. It will remove the trimethylsilyl ether and turn it back into our alcohol as a product. Right, so it removes this guy and we end up with our alcohol. So acid or fluoride, what is fluoride again? Fluoride's just again, how do we get that into a reaction? So we usually use something called TBAF, which stands for this tetrabutyl ammonium fluoride. Again, just note that we've got our protecting agents, we've got our Grignard reaction, and then to deprotect and remove that protecting group, we're essentially just going to use this TBAF. It's the source of fluoride. It's what, we always use to, I guess, deprotect things. Okay, so again, 3 separate steps. Protection. These guys are how you're going to protect your alcohol. We've got our Grignard reagent production as well as reduction in the middle here. And then at the end of the day, we still have that trimethylsilyl ether. We need to deprotect it and turn it back into our alcohol using TBAF. Okay, so let's go ahead and utilize this in an example. Again, if you want to go ahead and try this on your own, I would pause the video now and then come back for the answer. But ideally what we're going to try to do here is we have our starting material, or we have something, right? So this is going to be what forms our Grignard reagent. So this forms our, I'm just going to abbreviate GR. And we're going to want to use that to make this guy as our final product, okay? And so the question is, how do we go from here to here, all right, using everything that we've learned thus far? Okay, so ideally what's going to happen is if we just took this as is, right, and we reacted this with magnesium, the Grignard reagent that we would form would look something like this, right, where we'd have the magnesium, the bromine, this would be the polarized bond, right? So this would be the polarized bond, and so this carbon would contain essentially all of those electrons. That would be our nice nucleophilic carbon, our carbanion, or our carbide, right? So you may wonder, well, what happened to this guy out here? I'll go ahead and draw this guy as well, obviously. But ideally, in a perfect world where we didn't have to consider this protecting, deprotecting, this is what we would do, right? We would then take our Grignard reagent and we'd react it with an aldehyde or a ketone to get whatever product we're wanting to form over here, right? So notice that in that reaction, it's going to be this carbon that's forming a bond to another carbon, right? And that carbon it's forming a bond to is going to end up with an alcohol group also attached at the end. Right, so notice that the bond that we're going to form in this reduction reaction is between this guy and this guy. And so as a result of that, the things that are already there are these guys here as well as this, but this is going to be in the form of a ketone, right? So ideally, perfect world, we take our Grignard reagent, we react it with our ketone here. So we've got this guy. This essentially, again, attacks the carbonyl carbon, and we end up via a couple different more steps, obviously, here, right? Okay, but unfortunately we can't do that, right? Because there's a big no-no over here in the form of this alcohol group. If we were to take this guy and we react with magnesium and form our Grignard reagent, just like we had just mentioned, instead of this attacking our ketone, all this would do is deprotonate this, and we'd be essentially wasting all of our Grignard reagent, okay? So because of the presence of that alcohol, we have to introduce a couple more steps to account for that, right? So the first step in this is going to be taking our starting material that's going to form our Grignard reagent, and it's going to be going through a protecting step first, right? So our first reaction here is going to be taking this guy, and we're going to protect it using our protecting group, that trimethylsilyl chloride, right? So we're going to take this guy, this is going to be TMSCl, and then again, this is going to be triethylamine as a solvent. So this is going to be step number 1. That's going to add a protecting group onto the hydroxyl, right? So we're going to be left with this guy, oops. And then this is abbreviated OTMS. Draw everything back in. So again, this first step is protecting. Once we have our protecting group on, now we can form our Grignard reagent, right? So in the second step, all we need is magnesium metal to do that. Try to make these a little bit more sharper. MGBR. We've got our aromatic ring, and then we've got our OTMS. Once we formed our Grignard reagent, then in another step, we're going to react it with our ketone. Again, we've already recognized that these bonds are present in that ketone, and the carbon that's being attacked is going to be the carbon that has the carbonyl on it, right? And so we're going to take this guy. It's going to react. We're going to form as a product this guy. Again, in that first step, we can't add water, right? So we're going to end up with that alk oxide ion. Let me go ahead and finish drawing everything in. We've got this guy, we've got OTMS. And then we're also missing another carbonyl here, or another carbon bond from this guy, become this guy, and this guy. And then finally, we need to protonate that, so we'll add water. And we end up with something that looks like this. We've got OH, we still have OTMS, right? And so again, the magnesium, the reduction, and then the protonation, that's all part of that whole formation of Grignard reagent, and then reaction with the ketone. And so now to get this thing off, all we need to do is deprotect. So to get back to here, we need to deprotect. And again, I'm not going to go into the mechanism behind this, but to do that, we either need acid or a source of fluoride. And our common source of fluoride is that TBAF. And so that's it. All right, once we react that protecting group with TBAF, it'll remove it and replace it again with the hydroxyl of the alcohol. And so those are all of the reagents. And note that all of these are going to be their own separate step, right? So the first step is that protection, right? So we have T, that trimethyl silyl-chloride, TMSCl. And again, this is in triethylamine. The second step is formation of our Grignard reagent. So this is just magnesium metal. And a third step, we're going to react it with our ketone. So let me actually draw that a little bit clearer. So we'll go below the arrow. This guy. Fourth step, we need to protonate our alk oxide. So this is just going to be water, or again, any source of product solvent. And then fourth or fifth, we need to deprotect, and we're going to use TBAF to do that. All right, so all of these reagents are going to take this guy and turn it into this guy overall. Okay, that's fun. All right, so I'm going to stop here for this part, and then I will finish up the rest of this in the next lecture. So go ahead, and I'll probably try to start in the homework once I upload it. And then we're getting close to the end, so fingers crossed that we actually reach it